right, well, welcome to the lecture for chapter 2. Um, of your textbook. And I'm going to start off with an example. And the example is you're going to toss 3 coins. Okay. So that's the experiment. And that's what your book refers to as an experiment. Okay. We don't talk about random variables until later in the book, but I'm going to define your random variable. And it's random because we don't know how many of the coins will land heads. So this is going to be the number of heads out of 3 coins. Okay. This calculation is going to be a theoretical calculation. In that the way we calculate it is that the probability of an event is going to be the number of ways E occurs divided by the total number of outcomes. Okay, so I'm going to fill out this chart. And it's a table for the outcome of X versus the event in the sample space S. Okay, and S here, this corresponds to sample space. Okay. So the number of different values for X, we could get no heads, we could get 1 heads, we could get 2, or all 3 of them. And here, our event that corresponds to 0 is just going to be tails, tails, tails. That is, the first one is tails, the second one is tails, and the third one is tails. Then, for X equals 1, that can occur in more than one way. It can occur in heads, tails, 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 heads, tails, or it could be tails, tails, heads. Okay, for 2 heads, it can be heads, heads, tails, heads, tails, heads, or tails, heads, heads. And for the last one of all heads, it can be heads, heads, heads. Now I'm going to put down one other column here, and this is going to be called P of X, the probability. After all, the probability is the number of ways it occurs. The number of ways it occurs is listed for X equals 0 is just going to be tails, 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 divided by the total number of outcomes. We wrote it down. That's 8 of them. So 1 here, 3 here, 3 here, and 1 here. So I could do 1, there's going to be 3, there's going to be 3, and there's 1. So if I wanted to write down this probability, this would be 1/8. Okay, there's 8 outcomes when I add the 1, 3, 3, and 1 together. This will be 3/8, this will be 3/8, and this will be 1/8. There's a couple of things I'd like to point out about this. So the sample space S is all of these events. Okay, let me just go back a little bit. Sample space is all of this. It's all 8 events. This is the sample space. And that is the set of all possible outcomes. Okay. Now, the other thing that I'd like to notice here, and this goes back to the axioms of probability, is that notice this probability right here, the sum of all probability that's 1, and P of X is always greater than 0. Okay. So things are getting a little crowded here, so let me rewrite that. Okay. And so let me just write that. Okay. And this is true. For P of X to be a valid probability density, we need 2 things. One is that the sum of all the probabilities is greater than or equal to 0, less than or equal to 1. 2 is that the sum of all the probabilities, that is from 1 to 3, but I'm going to write from minus infinity to infinity, of P of X, the total probability adds up to 1. Notice for probabilities less than 1 or greater than 3, the probability is 0, so this formula still holds. And this is also in chapter 3, just FYI. I'd like to go back to that example and let me just discuss very briefly what an event is. So an event, let me use a different pen here. event is any subset of the sample space. Okay. So for example, an event E could be the event of one head, and that is exactly equal to the outcome x equals 1. We could write that as heads, tails, 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 heads, tails, 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 heads. That's an event. So it's a subset of the possible outcomes. Notice here that P of E is equal to 3s, and that's P of x equals 1. Okay. There's something else I'd like to define here, and that's the complementary event. This is the set of all outcomes in the sample space S, not in E. So for example, if E is the set that E is the outcome of exactly one heads, then the set of outcomes in S, not in E, are going to be tails, 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 no heads. Okay. I could go and look at two heads, 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 tails, but that occurs in several different ways. Heads, tails, heads, tails, heads, heads, and also all heads. Okay. Notice here, P of E complement, well, that's 1, 2, 3, 4, 5. That's 5 ace. And we can also notice, well, the probability of the complementary event plus the probability of the event, that happened to add up to 1. That's always true, just by definition. Probability of E is everything in E, and probability of E complement is everything in S, not in E, so it makes sense it adds up to every possible outcome. And you arrive at this complement rule. And the complement rule just says this: the probability of E is going to be 1 minus probability of E complement. Okay, that's your first rule of the day, and it's the first of many. Okay, now I want to give you just a quick example of unions and intersections. So I'm going to let the event F, that will be the event the first coin lands heads. Let me write out what F is. F is going to be heads, then it could be heads, then it could be heads again. The first coin has to land heads. Heads, tails, heads. Can be heads, heads, tails, and it could be heads, tails, tails. Those are the 4 outcomes associated with F. Let me write down what's called the intersection. And this is written as F union, F intersect E. So that is the set of outcomes that occur when the first coin lands heads and there's exactly one head. Well, that has to be heads, tails, tails. That is in the event in both E and F. So that's what an intersection is. It's the set of events that are common to both F and E. And probability of F intersect E, well, that's 1/8. Okay. Okay, now in addition to intersections, there's unions. And this would be written as F union E. And that's the set of all outcomes in E. And this will be OR F. Okay. And if I had to write this out, it's going to look like this. It's going to be heads, tails, tails, heads, heads, tails, heads, tails, heads, 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 heads. So I just wrote down every outcome in F. I don't count this event again because it's already counted in in F, so I don't count it in E again. Instead, I'm going to start listing off elements in E. So that's exactly one heads. Tails, heads, tails, because it can be in F or E, so I'm listing off the things in E. Then it can be tails, tails, heads. And that's everything. So if I had to write probability of E union F, well, let's see. This is 1, 2, 3, 4, 5, 6. That's going to be 6 ace. Notice that this is not equal to probability of E plus probability of F. Probability of E, let's see, that was 3 ace. Probability of F, that was 4 ace. Let's see. I would be counting, probability of E would have 3 events, which would include the heads, tails, tails. So probability of E would be this. Okay. Probability of E would be that. That would be E. Then if I was to look at probability of F, it'd be all of this. So that'd be 4, and that'd be F. And wait, I've counted heads, tails, tails twice. So that's exactly the amount by which I'm off by. So what we basically concluded is this. There's this general addition rule. and it says this: the probability of E union F is going to be equal to the probability of E plus the probability of F, but if they share an intersection, I have to subtract that. That was one event that they had in common. Okay, and let me just draw this for you in terms of a Venn diagram. Here it'd be E, and here it'd be F. And the intersection would be in E intersect F. Probability of E would be all of this stuff. Probability of F would be all of that stuff. So I've counted the intersection twice. So this says I'm just going to remove it. Okay. So that's your second rule for the day, is the general addition rule. Okay. Okay. Now, let me just give you a quick example here. And this example is going to be on cats and dogs. So let's consider the data. Okay. So here's going to be cats data, and this is going to be none. And then this is going to be yes, which is one or more cat. And then here's going to be the dog data. And there's going to be none. And then there's going to be the yes category. Okay. And consider this data. So I've made this perfectly symmetrical. I'd actually like to change that. So I'm going to just change this by a little bit. Okay. And let's say there we go. So I'm going to add a column here. This is going to be the total. These are actually called the marginals. So when I add this row, I'm going to get 600. I'm going to get 400 there. And when I add this column, I'm going to get 600, and I'm going to get 400. The grand total is not going to be 2,000. This plus this plus this plus this. Instead, it's just going to be the sum of the interior. That's 1,000. So here we're going to use observational probability. And that is calculated by the observed number of outcomes divided by the sample size. Here the sample size is 1,000. And I could ask you, for example, what is the probability an individual has a dog? So So probability of yes to the dog. Well, how many people had dogs? If we go back, okay. If we go back here, we can see that the yes category, 300 have yes dogs, and then an additional 100 have yes dogs, but also they have cats. But all we care about is that the fact that they have a dog. So that's going to be 400. So it's going to be the 400 divided by 1,000. I could write that as 300 plus 100 over 1,000. Okay, so 40%. Okay. Okay. I can ask, I can ask, what's the probability of dog or cat okay, and I could just go to the table. In this table, I could say, well, how many said yes to having a dog or cat? That'd be 300 plus 100 plus 300. So it looks like 70% have a dog or a cat. So I could do just this 700 over 1,000, or I could do the addition rule. Addition rule would say I could do probability of dog plus probability of cat minus probability of both. Okay, and if I did that, well, I'd have to go back to the table again. So probability of dog is 40%, probability of cat is 40%, and probability of both, that's that 100. So going back here, I could do 400 over 1,000 plus 400 400 over 1,000 minus 100 over 1,000. And again, we'll get 70%. Let me ask you a slightly different question. Okay, and this is going to be the slightly different question. Okay. So if an individual owns a cat, what are the odds they own a dog also? So this is called a conditional. And we've conditioned on them having a cat. So probability of dog, and this will be given cat. Okay. So we're told we can calculate probability in a number of ways that we can get a dog divided by the total number of outcomes. Now let's go back to this data. Well, probability of dog is not going to be 40%. Is going to be out of the possible outcomes. It's not possible to have 300 yeses and to have no cats. None is not possible. Instead, it's asking, out of the individuals with cats, that's 400 of them, what's the probability they also have a dog? That'll be 100. So it's going to be 100 out of 400. So it's not the total number of outcomes that are possible is not the 1,000. It's only the 400 that own the cat. And out of the 400 that own the cat, only 100 have dogs. So it's a 25% odds, which is lower than the 40%. Okay? And the fact that it's not 40% tells you that they're dependent events. Okay, so we have two things going on here. So I just want to point out that this 100 out of 400, that 100, they had to satisfy the criteria that they had a dog and a cat. So that would be 100 out of 1,000 divided by the 400 out of 1,000. And here's the key point. Probability of A given B, that's going to be the probability of A and B, probability of cat and dog, divided by probability of cat, which is B. Okay, this is your conditional probability. If probability of A given B equals probability of A, then A and B are independent and otherwise they are dependent. Okay, so this is a key definition. Now let me give you one more thing. Probability of A given B, that's also written as A bar B, that's equal to P of A intersect B divided by P of B. Probability of how A and B both occur divided by the probability of B. This implies that probability of A intersect B is equal to P of B times, just clearing the denominator, A given B. And this is called the general multiplication rule. Okay, so I'm going to stop here, but we're going to still have more examples. There'll be a part 2 to this lecture in chapter 2.